Hello, sort of a flash forward. While every other one of those videos was recorded in the early summer of 2019, I'm recording this video on August 10th, 2023. Basically, there was a question that Miss Formaker and I changed several years ago, back in probably like in that range of like 2020 before the stuff started. And basically we just never adjusted on the ESQ model. So I want to make sure that you've got support for that one. I don't envision this question, other than maybe part C or D, as being something that you're going to need a ton of attention with. But at the same time, like again, I want this resource to be complete for you in case you're looking for some support before your first ESQ, which is a few weeks away for us, but in general could be tomorrow for all I know. Who knows when you're watching this video. So as I've done with all the other ones, I'm going to work through the questions on the ESQ model, the new updated ones that I will add to the updated ESQ model in Google Classroom, and make sure that you kind of know the strategy, know the lingo, and that you're comfortable attacking these things. As with the other ones on this ESQ model, there's a few questions. I think there's 3 questions that all kind of fit the form that would show up on there, although C is a pretty tough question. I'm not going to lie about that. And then P, which would be a plus question, which is pretty basic but has some like unique twists to it. So rather than keep talking about it in general, I'm going to go ahead and just dive into the problems. The first of those problems is going to be question 7A. 7A fits the structure of these problems for question number 7, which is going to ask you to evaluate a one-sided limit of some kind. In this case, question A says that you are supposed to evaluate the limit as x approaches 4 from the left side of g of x if g of x is given by the piecewise function shown at right. So our job here is to determine what that limit is if it exists, although with one-sided limits we're typically going to find that that limit does exist, and then of course to evaluate that limit. So we're trying to evaluate a limit. Our answer here should be a number, although there are some rare situations in which case this would not be a number. This is definitely a number. So a couple little notes here. Depending on when you're watching this comment may or may not add anything to your understanding, but basically both this and this are exponential functions. Therefore, they're both continuous on their own. So just kind of worth pointing out, there's not going to be any funny business anywhere except at the boundary. And because one branch is defined for x less than or equal to 4 and the other for x greater than 4, our boundary is 4, which conveniently or inconveniently is what we're checking the neighborhood of. We're interested in what's happening around x equals 4, but we're specifically interested in what's happening around 4 as we approach from the left side. So the important thing to note here before we start anything out, and again, this is meant to sort of like help you with the concept in general, so I want to make sure that that's gotten in your head. Basically, this is describing the behavior of the function from the left side. So it excludes all values of x greater than 4, and it only asks us what's happening when, and specifically when x is approaching 4 from the left side, which is to say what's happening when x is less than 4. Where is this function going? Where is g of x going when x is less than 4? So you can kind of imagine visually, although this isn't what ours is going to look like, I'm just making random pictures here, that if we've got this piece here going on, I don't know, if we have something like that, we're interested in what's happening as we approach 4 from the left side, assuming of course that this was 4, we're looking to see where is it going down here. Like that's the y value we're looking for. It doesn't matter whether it's included or excluded at all, just what's happening as we approach there. So in other words, what does the function do when x is less than 4? Well, the good news for us is that we have what's happening when x is less than 4. Specifically, though, we have when x is less than or equal to 4, but it doesn't make any difference. It's the same ball game here. The or equals to doesn't affect our answer in any way. It could be in either of those branches or both. Well, it can't be on both. That'd be wrong. Or neither, but it would still have the same one-sided limit value. So in this case, when x is less than or equal to 4, or specifically when x is less than 4, g of x is given by 3 to the x minus 11. That means when we go to evaluate this limit, as x approaches 4 from the left side of g of x, we are going to evaluate by plugging into the left-hand branch. We're going to use this branch because 3 to the x minus 11 is how the function behaves when x values are smaller than 4. So we'll actually just put 4 in there. So basically we'll have 3 to the 4th minus 11. Be careful you don't accidentally write that this is equal to 1 and see 12 minus 11. 3 to the 4th power is 81, and 81 minus 11 is, of course, 70. So the one-sided limit in part A of question number 7 on the ESQ model is 70. So again, it's all about identifying which branch of the function to work with, and then of course plugging correctly into that branch of the function. Remember though, by the way, you don't have to simplify, at least in our course and on the AP exam. So if you weren't sure what 3 to the 4th was, if you had any hesitation, just write that. This is acceptable as well. Like there's nothing wrong with that piece as well, except I made it a little bit narrow. So there we go. There's the first of our questions. Again, identify your branch, plug into that, evaluate. The second problem we're going to address is going to be part B of question number 7. This one asks us, in this case, to evaluate a right-hand limit, which just kind of gives us a nice complement to the first one, which was a left-hand limit. So as you'll notice here, we're being asked to evaluate the limit as x approaches 0 from the right side. That little plus where the exponent would normally be would indicate that we're approaching from the right side. And it's of the function h of x, where h of x is given by this piecewise function that has two trigonometric behaviors defined for x less than 0 and x greater than or equal to 0, respectively. So just as I mentioned in the first video here, it's important for us to establish, based on which one-sided limit we're looking at, which relationship or what specific x values we're looking to consider. So basically in this case, we are interested in figuring out what's happening here, or I'll put it this way. We're interested in putting it this way and analyzing h of x, but specifically h of x when x is greater than 0, because that's what's meant by the limit as x approaches 0 from the right side of h of x. We're interested in only one part of the behavior, so I don't know if this is quite perfect, but imagine that it is for a second. We've got this function, and I know something like that. Basically, we're interested in what's happening as we approach from the right side. So using those values of x that are larger. And obviously, since tangent's involved, this is a discontinuous function at many spots. But for the moment, like, we're interested in 0, so we're fine there. So now, of course, what does that mean? Well, we want to use the section where x is greater than 0, which is going to occur right here. So we're going to be evaluating this limit, this one-sided limit, using the tangent portion. So let's go ahead and do that. We want to evaluate the limit as x approaches 0 from the right side of h of x. That's going to involve us plugging 0 in, or substituting 0 into the function. So pi over 0 plus 4. That's going to give us the tangent of pi over 4. And tangent of pi over 4, I think I drew this in the written solution, so just to be safe, pi over 4 is the same thing as 45 degrees. So we have a triangle in quadrant 1 that we can use to draw and represent this. If pi over 4 is our degree, or is our radian, then 45 degrees will be our degree measure angle. We'll have adjacent, opposite, and hypotenuse. And since tangent is opposite over adjacent, this will be 1 over 1 equals 1. So this limit is actually equal to 1, or specifically this one-sided limit is actually equal to 1, which is just sort of interesting. So there's our second one as well. Our third question, which I think is a good representative, sort of the only wrinkle we'd throw onto the non-plus ESQ in Calculus AB, is going to be question 7c, which asks us to evaluate a one-sided limit. Notice it does ask us to evaluate the limit as x approaches -2 from the left side. Note that little minus sign up in the exponent spot. But it wants us to evaluate it for not a piecewise function, but a rational function. So a function that you've sketched before many times. I always call them flying squirrels, although it's a total stretch, I completely admit that. But effectively, we've got a single function here that has some distinct behaviors to it and some interesting discontinuity baked in as well. And our job is to evaluate a one-sided limit for it. And I will completely confess here that although up to this point, a and b were both finite values, like we got numbers as our answer, as soon as we introduce vertical asymptotes into the equation, one-sided limits suddenly become a little bit more expansive. Plus or minus infinity comes into the picture suddenly. And this is a case where our answer will be plus or minus infinity. Just remembering sort of the classic parent graph from this group, and just remembering that it looks like this, points you to why a vertical asymptote can create some infinite behavior for us to analyze. And so that's exactly what we're going to look at here. How do we evaluate this answer? Other than just going plus or minus infinity and guessing. Don't recommend that. Not your best strategy. So the strategy that I'm going to use here, there's a couple different ways to do it, and I'm going to show you both of them. In fact, I'll go ahead and kind of draw a line down the middle, just because your approach may vary. I've seen different students sort of take to different approaches. The first of those approaches that I see most often is to use a graphical approach. And what that means is basically draw something. which I think was actually an iPhone app/game for a while. But beside the point, you draw a diagram or a graph of this function and check its behavior that way. So in this case, I'll start by sketching a pair of axes, a coordinate plane as best I can. It is fairly coordinate plane. It's not very exciting or fancy in any way, but there we go. There's our stuff here. And now I want to sketch this function up here, which is given by 4 over x plus 2. So in order to do that, we've got to think about a little bit of information. You do have to remember sketching rational functions a little bit. I would hope the most important piece of information or the most important behaviors stick around. So the first of those would be a vertical asymptote. That's what you get when x plus 2, the denominator, equals 0, and the numerator doesn't, by the way, but it's just a constant up there, so we're okay. There's a vertical asymptote at x equals -2. So you probably suspected that was going to be the case because the one-sided limit asks about -2's behavior, just from the left side, but still at -2. And in fact, that's exactly what's happening here. And if you're looking at that vertical asymptote, by the way, and going like, why in the world is it so crooked? It would be very specifically because my microphone is blocking that space, so I apologize. So there's our vertical asymptote. Likewise, we could talk about the horizontal asymptote, or the and it's basically like what we get when we divide the numerator by the denominator and then evaluate the limit as x gets really, really large. In our case, I'm hoping you'll remember the degree comparison. Since the degree in the numerator is smaller than the degree in the denominator, our horizontal asymptote will just be 0. Like imagine x gets really, really large, or really, really large and negative, and you'll have a small positive number divided by something really, really large, which effectively gives us 0. So there's also a horizontal asymptote in play here at y equals 0. And then last but not least, we need to evaluate and find where the graph itself is going to land in this thing so we can check its behavior. So to do that, I'm going to pick 2 points to kind of check things out at. The first one I'm going to do is to give me the y-intercept. So if I want the y-intercept, I'm going to plug in x equals 0. Looking over here at our graph, or our function, in order to make the graph, if we plug in x equals 0, y is going to be 4 over 0 plus 2, which of course equals 2. So we're going to have a y-intercept of 0, 2, which is of course positive, so it's somewhere up here, and it looks like we're going to get a branch up there, but let's do one more just to be safe. And then second, we're going to have some number comma 0 for the x-intercept. In order to do that, we set this whole thing 4 over x plus 2 equal to 0, but you might already recognize that this will never equal 0. Basically, the only way to make 4 divided by something equal 0 is if the denominator is infinity, and if it's infinity, it means we never touch it. Finite is a concept, not a finite. Infinity is a finite concept, not an actual finite value. So we have to be a little bit careful here. Specifically, this tells us that there is no x-intercepts, or there are no x-intercepts. So cool, that's what we got. So from here, just to kind of match it, basically this is going to give us enough to sketch a single branch of the function. And unfortunately, that's not enough for us to finish the problem because this is going to give us the limit as x approaches -2 from the right, and we were tasked with finding what's happening from the left. To find what's happening over on the left, you got 2 choices. You could go through and plug in any number smaller. So specifically, you could plug in like x equals -3, because if you do, your y value will end up being, if I do this correctly, 4 divided by -3 plus 2, which is -4. So basically our other point is going to be somewhere down here, which gives us this as our function's behavior. So there's our sketch. We've got it ready. By the way, flying squirrels forever. Good job, us. Setting that aside, though, we want to figure out what's happening specifically as x approaches -2 from the left. On the left, that would be x value smaller than -2. Notice that we are going downward. We are headed below, like just down. That's telling us that the limit is approaching -infinity. So our answer here would be -infinity. And with one-sided limits, we don't accept a does not exist answer. The one-sided limitness allows for this negative or positive infinity to be precise. So it's probably more information you need, but just want to be accurate. Now, I said there was a second way to do that and to kind of get a sense of what's happening. So I do want to just quickly expose you to what that way is. I typically don't write out this method at all. I just think it through a little bit to confirm my intuition in my head. But, you know, your mileage may vary. Specifically, it revolves around the idea that we're talking about what happens as x approaches -2 from the left side, because that tells us that we want to plug in numbers or values for x that are smaller than -2. So what I'm going to do is I'm just going to plug in 3. And like when I say table, I mean I'm going to take those 3 x values and plug them into a table of values and just see where they're going. Those values I'm going to plug in, since we need to stay below -2, I'm going to put -3, -2 and 1/2, and then -2, and I just want something that's really close to -2 but still on that side. I'm going to do -2 and 1/10. So the idea is these values are getting closer and closer to -2. Not that we'll ever get there because there's a vertical asymptote at -2, but that trend will tell us some information about which direction this function is going. If the values are getting bigger and bigger as well as more and more positive, or bigger and bigger while still being positive, we would say the limit approaches positive infinity. If those values are getting smaller and smaller, but also negative, then we will say that the limit is approaching negative infinity. So in here, we're literally checking what happens with 4 over x plus 2. So going one at a time, 4 over -3 plus 2. And again, remember, like I said, I do this in my head. You don't have to write out the table, but this is the thinking behind that strategy. This gets me -4. If I plug in -2.5, that will be 4 over -2.5 plus 2, which is going to be, if memory serves, let me make sure I do this correctly, this will be -1/2, which gives us 4 over -1/2, which is -8. And finally, just to kind of like implement or incept this idea a little bit stronger before we call it, this will be 4 over -1/10, and that's going to be -40. So notice with these y values that the y values are growing larger, but also staying negative. This is code for us seeing that those y values are approaching negative infinity. Basically, if we went further, if we made smaller and smaller fractions here, they would keep flipping up and still being doubled, and we would get closer and closer to this concept of infinite size. So for us, that's just another approach that confirms the limit as x approaches -2 from the left side of 4 over x plus 2 is negative infinity. So you have 2 separate approaches to take. It's your call which one to go through. I think that a lot of students, a lot of you will likely have some good intuition about this problem anyway, and your own method of handling it. Of course, that's a-okay. I'm just choosing 2 that sort of have spoken to me. If I don't speak now about them, like when am I going to get a chance to? So that's the third question. Cool stuff. The final question we're going to hit, I just kind of like. I really like these questions because it's not difficult, like difficult calculus-wise, like conceptually. But what's difficult is it asks you to do some other sort of problem-solving stuff alongside a traditional calculus problem, maybe remixed a little bit more interestingly. So in this case, we're told that the limit as x approaches a from the left side of p of x is equal to 2 times a. So that's just some information we have about some function p of x. Now it specifically says p of x as this piecewise function over on the right side, and we're supposed to figure out what are all values of a. Like what are the possible values that a could ever take on. And to do this, I'm just going to start, I'm going to approach this problem the same way students would if you weren't comfortable with it, if you weren't sure what it was asking, and that is just to start the problem. Do something about it that you understand. And I would argue that for all the verbiage in this problem, it says the limit as x approaches a from the left side of p of x. Forget about 2a for a second. It says the limit as x approaches a from the left side of p of x. So if we want to check the limit as x approaches a from the left of p of x, then we're going to have to use the values of x that are smaller than a. Well, where those occur is right here. It also occurs at a, but we're just going to set aside the point itself for a second. So when x is less than a, p of x is given by ax minus 15. So for us, we need to evaluate this limit using the correct branch. It is going to be that branch, but specifically it's going to be that branch when x is approaching a. So here's how that's going to look. We'll have a times a substituted for x minus 15. Last but not least, it also tells us in the problem that this limit we're investigating is equal to 2a. That means this entire expression is equal to 2a. And what we've just done is created an equation in just one variable, a. Everything in here has the same variable. It means we should be able to solve it, give or take like an incorrect degree or something. So in here what I'm going to do is I'm going to simplify it a little bit more. Let's do it. A times a is a squared minus 15 equals 2a. By the way, sort of an interesting, like, sort of bit of foreshadowing here. It says, what are all values? That sort of suggests that there might be more than one, and there are two in this case. We have a squared minus 15 would have to equal 2a. Otherwise, the left-hand limit as x approaches a wouldn't be equal to 2a, or it wouldn't work that way. And so now we just need to solve this equation. So what I'm going to do is I'm going to subtract 2a from both sides. Negative 2 ain't bad if you try. Okay, thought I had something. I didn't. But in any event, none of the like terms combine because there are no like terms here. So there's our equation. And frankly, like, I see a classic factoring problem. This factors into a minus 5 times a plus 3. And from here, that's going to leave us two values. It's going to leave us a equaling negative 3 and a equaling positive 5. So there are our two values. I would invite you, if you're at all skeptical here or just interested in a little bit of an extra challenge, to take both those values, plug them into the function up top, and verify that the limit as x approaches a from the left side of p of x does in fact equal 2 times a. So if a was negative 3, that limit would have to equal negative 6. If the a value was 5, that limit would be equal to 10. So just some interesting information to kind of put out there. But most importantly, that's going to end the video. Basically, we went through all 4 of the problems on the ESQ model for Calculus AB, and hopefully gave you just enough insight for you to be able to dive back in and get this one right. I do think this is a really approachable question that most people get correct several times, if not every time over the course of the quarter. And we're not going to change that, but obviously there are wrinkles that are still able to sort of crop up when you're working through these problems. So hopefully these videos helped you confront those and actually approach them and work through them accurately and comfortably. So that's going to do it for me. Feel free to like and subscribe if that's a thing that you're into. No worries if you don't, but I will see you hopefully at some point at school or in a review session or something else. See y'all later.